Hi everybody, my name is Dave Grizzanti, and I'm going to be talking about avoiding the pitfalls of autoscaling with constant work. So as I said, my name is Dave Grizzanti. I am a principal engineer at the New York Times. Previously I was at Comcast, and I actually just joined the Times about 6 weeks ago. So this is a very recent change. Shout out for the Times colleagues in the audience. So I actually took this picture this morning. This was an impromptu edition. I thought the sunrise was too good not to add, so that's the reason for that picture. But so the talk I'm going to give today is around topics and work that I did at Comcast, not at the Times, obviously, since I've only been there 6 weeks. And it's really around some of the struggles and things that I thought about while I was working on platforms at Comcast, and really around time series metrics, work that I did with open source tooling there, and our observability team. So I'm going to go through some theory stuff, some background on that, and at the end there'll be a short, not live demo with notes and a few other things. So let's dig into it. So while I was working on this talk, and probably for the last couple of years, I've been thinking a lot about this concept of softwareilities, which I show a bunch of them up on the screen here. And these are really non-functional software requirements that we as engineers have to deal with a lot, but are often not included in product briefs or product requirements. They're things that are kind of expected that we understand how to deal with, that are often much more difficult to deal with than building business logic. But they're really important aspects of the systems, and I'm going to be talking about a few of these today in more detail. So one thing I want to point out is this book by Martin Kleppmann. I know Martin is a frequent strange looper, but I came across this book earlier in the year while I was working on this talk, while actually I was looking for resources to prepare for interviewing. And if you're going to do any system design interviews, I recommend reading this book. It goes into detail on lots of things, lots of system design stuff, but really it has a good framing around three of those ilities that I mentioned earlier: reliability, scalability, and maintainability. So I'm going to talk about scalability mostly, but also talk a little bit about reliability in the beginning too, just to give some kind of background and definitions. So a definition for reliability, quick, just to kind of set the stage. So reliable systems should continue to work correctly, performing the correct function at the desired level of performance, even in the face of adversity, hardware, software, or human error. So let's talk a little bit more about these three types of faults or errors: hardware, software, and human. So hardware faults, I think commonly us as engineers think about those things as like server failures, disk, physical things in servers that might fail, but can be thought of in the non-software world too, like things like power grids. We've been having lots of issues with power grids recently due to climate change, either heat or cold. So this is a picture of, I think this is Austin, but it's one of the Texas power grids before and after an outage they had last winter, because Texas doesn't normally get very cold winters and snow. So this is example of hardware reliability issues. On the software side, there's a whole plethora of software faults that we kind of deal with on a daily basis. But cascading failures is something that I'm going to talk about specifically today. And this is the idea where a small fault in one component triggers faults in another component and so on, right? You have this kind of domino effect. And last is human error. And I think this is probably the biggest one that causes most of the outages that we're used to anymore, oftentimes with configuration errors. So humans are notoriously unreliable. We make mistakes all the time. And a study found that about 10 to 25% of outages were caused by hardware faults. The rest were caused by humans or software. So next, let's talk about the other ility, scalability. So as systems grow in data volume, traffic volume, or complexity, there should be reasonable ways of dealing with that growth. So scaling something most engineers lately have dealt with as we kind of get into this more DevOps model. Engineers are doing software building and a lot of infrastructure work. So I'm going to talk a little bit about just kind of general scaling of systems, go from like a simple example to a more complex one to kind of go through what that looks like. So two common examples I'm going to talk about now. So vertical scaling, this is the idea that you're increasing, the size of the instance. So CPU, RAM, et cetera, you're making the instance bigger. And then horizontal scaling is another example. This is the idea that you're taking some set of servers that you're running and just adding more, right? This is pretty common with microservices or systems that don't necessarily store a lot of data, so they're kind of stateless. So these are two common examples, and I think autoscaling is something that people want to achieve generally with scaling because it gives you a lot more flexibility. So autoscaling is a technique for dynamically allocating resources based on demand or schedule. I think it was popularized mostly by AWS originally with their autoscaling groups, and this idea that you can build plans around automating how different groups of resources respond to changes in demand. And this can be things like a schedule, like I want to scale up my servers in the morning because I know that I have more traffic between 8 and 5, and I want to scale them down at night. Or it can be more elastic than that. I want to scale them based on CPU. Just go up. Yeah. Can you still hear me? Yes? Yeah. I've got to shout a little bit. Okay, oh, there's back now. CPU and like watch to monitor your servers and say when something goes up or down. I want it to respond to some change in what's happening in the environment. So let's go through like a workflow of what that would look like. So here's a very simple example. You have some people accessing a service that you built over the internet with a single server. This might be great for like a side project you're working on or like a GeoCity site in the 90s or something, but for people who get that or who are old enough. So this is something very simple, single point of failure, right? If it goes down, it's going to affect your users. So you can scale that to better, put a load balancer in between. So if one goes down, then you still have something else serving traffic, but it's still kind of static. If it has regionality issues, if this site goes down or the data center goes down, your users are still going to be affected. So you can take that and do it across 2 regions, same deal, load balance things across. That's better. If you lose a region, you have a backup region. But in this case, the load balancer is probably still configured to have these 6 static instances. It's still not great. So if we expand that and we do something like the scaling pattern I talked about before, you can respond to changes. Like if the server goes down, it can get replaced because you have a minimum or maximum size. You can scale it based on desired capacity or scaling policies, et cetera. And then an even like maybe further example of that is I want to run this through some global load balancing with load balancers at each site, and I also want to have the scaling policies. So now you're like kind of taking that from a single all the way up to this kind of like common best practices example you would see for autoscaling, a microservice. So that's great. That kind of gives us a base kind of understanding of maybe how you would scale a common stateless software app in a public cloud. But based on the title of my talk, there's maybe some pitfalls with that, right? Cases where your software may not respond well or deal well with just simple autoscaling. So let's go over some of those patterns. So I showed this picture earlier, this cascading failures thing. So just to kind of level set, cascading failures are failures that involve some kind of feedback loop mechanism. So in distributed systems generally involve a feedback loop somewhere, and some events can cause reductions in capacity or increases in latency or a spike in errors, and this causes like a cascading failure in the system, makes the problem worse. And it's often very difficult to scale out of a cascading failure, because if you add more capacity, the servers are still getting lots of load, they may become saturated, increase latency, and really the only way to recover from it is to take your service down completely, shut off all the traffic, and kind of bring it up from scratch. And the potential for these failures, while you may not have seen them, is inherent in most complicated distributed systems, and it may just be a matter of time before one hits your system. So let's go over a few examples of cascading failures. So first one, accept an unbounded number of incoming requests. So I think it's common for people to scale their service out to receive an expected number of requests on any given day or any given time. So in this example, your service receives about 1,000 requests a second. You're running 3 servers. Each one can handle 500. You've got a little bit of buffer room. And without any latency, it's serving the requests. Let's say that jumps to 2,000, and with these 3 servers, you start seeing a little bit of latency in the requests. And you could just scale out to add another server, but depending on how much time that takes, your users are already feeling some of that pain because their requests are waiting in some queue. So really, one of the kind of possible potential solutions is set limits to the number of requests each instance can receive, and they'll shed their own load. So you're not waiting for the users to kind of hit refresh or wait for the response to come back, and then that thing kind of can cascade to the other instances you're running. So recommended to kind of limit the number of requests each instance can accept within the software you're building yourself, instead of just that load balancer or just using scaling policies. The next one is proximity-based failovers. This one's very common. I think almost every system I've worked on, the assumption is if I lose a region, we'll just fail over to the other region, which in reality probably works, but if your second region is not scaled to handle twice the amount of traffic, or you can't scale it up quickly enough, you could take down the second region as you kind of fail over. So some things to watch out for here. Make sure you control any kind of load failover you're doing, so it's not just cascading down and taking down all of your regions, or maintain extra capacity everywhere in the off chance that you want to deal with these regionality failures. And the last one is long startup times. This one isn't as common, but in one of the systems I'll talk about later, this is common. So this is the idea that your service, when it falls over or at startup time, may take 5 to 10 minutes to read something into memory or read out of cache. And while that's waiting to start up, traffic's going to fall over to whatever other instances you have, maybe while you're waiting for that one to come back up, or you're adding another one, and that can kind of cascade and take down the rest of the servers that are running and kind of handling that traffic. So some possible solutions here is avoid these long startup times if possible. If that's not possible, then keep some warm or reserved instances on the side. Just even if they're not actively taking traffic, just keep them on the side, ready to serve traffic in the interim. So that kind of wraps up the cascading failures I wanted to talk about. And next I want to talk about a different pattern of work that's not this just kind of general scaling that can maybe help with some of these problems. So it's called constant work. I think when constant work works well, doing the same thing, regardless of what's happening in your environment, it's great. But obviously, depending on changing circumstances, that can go badly, like it does for Lucy here. So what is constant work, and how does it work? So a lot of the systems, a lot of the things we've been talking about now, large systems fail with rapid changes in load, and doing constant work can avoid this. Constant work is doing the same amount of work and type of work regardless of the load on your system. So I really got interested in this because the system that I was working on and running with time series metrics has a lot of different patterns for collecting the data, either like a push or a pull model. And this idea of constant work versus kind of the general scaling patterns reminded me of the kind of difference between these two things. So I want to go over some examples of this idea of constant work and kind of get into it a little bit more. So the pattern in general, I think, is AWS uses it a lot in a lot of their services. And when I was doing research into it, most of the examples I could find that were kind of more practical were all on their side. So the two of them I'm going to show are really examples pulled from many of their blogs. So this is an example, or this is a picture of the Route 53 health checks and how they work, simplified. So split into the control plane and the data plane. The control plane is really the thing that users interact with, right? When you're talking to the API to configure how you want Route 53 to work, you talk to the external API to configure your health checks and DNS records. But we're really going to talk about the data plane, which is the side on AWS's side that controls how all this works, and concentrate on the health checkers and the aggregators. So in the way Route 53 works is you're telling it, okay, I want a DNS record, and I also want some health checks for my resources. These are the customer resources on the left up here. And the health checkers are configured to, do a probe every once in a while to see if your resource is healthy. And that runs on a schedule, let's say every 30 seconds. So in this case, the doing constant work is avoid incurring delays by bounding the amount of work you do that request on a schedule, and on failure, don't retry. So perform the next check as scheduled regardless of the result. And the idea here is if they reach out to the resource and it fails, it doesn't automatically retry again. That would change the amount of work. So just do it again every 30 seconds, every 30 seconds. So the amount of work that those health checkers are doing is constant, regardless of what happens with the target customer environment. And then on the flip side, the checkers, kind of talking to the aggregators, those results are communicated asynchronously, and they transmit the complete state every time. So it's not like, oh, this customer resource failed, oh, this one passed. The status of all of their resources is transmitted the same every time. So it kind of keeps the rate of input at each of the different boxes bounded. So they're not changing the amount of requests that are being sent across to the aggregators or changing the amount of requests that are being done to the resources based on changes in their environment. So to kind of summarize some of these patterns, the key features are don't scale up or slow down with load or stress, don't have modes, do the same operations in all conditions, no variation, so less work in times of stress for better performance, and try to become more efficient while experiencing peak stress. And I think this last point is something we're going to talk about a little bit more in this idea of anti-fragility. If folks aren't familiar with that term, I'll explain that in a little bit. So one more kind of example of the constant work model to kind of make this a little bit more concrete. So another kind of simple service example, you have an app running through an AWS network load balancer with a service on the other side. And let's say you or somebody wants to add a third instance to that behind that network load balancer. So you might do that through automation, through Terraform or the CLI. But let's say you were a person going to the AWS console and you log into the console, you go to the AWS target group for the network load balancer and you add a new instance, or you remove one, or you add 3 or 4. You would say, okay, well, I assume that AWS is accepting those changes as I make the changes in the console. Like, oh, I added a new request, let me push that. But in reality, that would be very anti-constant work because it's doing things based on your requests. So what actually happens in reality is those changes are pushed through an S3 bucket, and the control plane for the load balancers just pulls that S3 bucket every second, regardless if things are changing. So it's asking, give me the state, give me the state, give me the state every second. It doesn't care if there was requests being made for changes, additions or deletions. So that work is bounded on either side. There's not any interconnectivity based on demand from the user. Back into this idea of anti-fragility. So I think most, if not everybody, is familiar with the term fragile, right? Things that are breakable, put stickers on packages that we send in the mail, things that are breakable. But what about this idea of, what does that mean? So this is a Hydra. For folks who are not familiar with the Hydra, the myth behind this is if you cut off one head, 2 heads grow. So right, the Hydra is getting stronger. It's growing with stress. As you attack it, it's benefiting. So this concept of anti-fragility is a concept that was developed by Nassim Nicholas Taleb in his book Anti-Fragile. I had read one of his other books called The Black Swan, probably 8 or 9 years ago, and found it super fascinating. He has a background in economics and economic theory, and this property is something, like I said, something he developed in the book, and describes it as a property of systems in which they increase in capability as a result of stressors. So as he explains in the book, anti-fragility is fundamentally different from the concepts of resiliency, which is the ability to recover from failure, and robustness, which is the ability to resist failure. So what are maybe some kind of real world examples of this to kind of plant the idea in your head? So for me, the best example that kind of helped me is not necessarily running. I'm a runner and I often get injured from running. So the idea of kind of building strength to prevent injury is something that I've been interested in in the last couple of years as I get older and injure myself more. So the idea of like weightlifting or making your muscles stronger is a very good example of anti-fragility, or our bodies are very anti-fragile, right? Like we benefit from stress. We put our muscles under stress by lifting weights. They get stronger, so the next time we lift the same amount of weight, it's easier, or we can lift heavier weights. Obviously, it's easy to put, not easy, but you can put too much stress on your body. It's only up to a point. But I think the human body is a good example of this anti-fragility concept. So how does this apply to software or to systems? So really, fragile systems are difficult to modify and can't cope with a changing environment. So even if they may provide some value in a stable, non-changing environment, but when faced with further stress, they can quickly turn into a liability. Robust systems could be implemented with certain buffers to handle change and stress, but when stress level increases, maybe it can withstand it up to a certain level without losing capabilities, but it doesn't adapt. A resilient system, which is probably what we mostly target, it is designed and implemented with stress in mind, and it has some adaptability features, but it can really only survive stress and change up to a point. So anti-fragile systems, which is maybe like the panacea of what we're trying to build, is created with change in mind, and it feeds from stress and change. It's much harder to create these systems, but I think some of the examples and kind of ideas in the constant work patterns, those systems can be anti-fragile. So they do the same or less work in times of stress. And maybe but a good example that I think with anti-fragile and systems is maybe like how we do stress testing or chaos engineering, right? We put our systems through these stressors to find weaknesses and make them stronger. So, kind of using stress testing and chaos engineering to find the weak points and make your systems more anti-fragile is a good idea. So I want to wrap up this section before I get into the kind of some of the more practical demo parts. So we talked about some scaling examples, pitfalls and cascading failures, and constant work and anti-fragility. So let's get into some more hands-on stuff. So as I mentioned in the beginning, most of these ideas and kind of thoughts were around in my head when I was working on time series collection. And the two things that my team had struggled with was really this idea of push or pull. And for folks who aren't familiar with the kind of tooling around this space, the thing on the left is an example of, or a picture from Prometheus, which is an open source time series collection system. And the other one is Victoria Metrics, which is another one. And they started off as kind of the two opposites of this kind of push and pull. Prometheus works off of a scrape model. So you're defining some targets and you're pulling metrics from servers. And I think some of the precursors to Prometheus and even post systems like Victoria assume you're just pushing metrics to some target system. So there's some pros and cons to each of these. I think pros from the Prometheus side is this like local model allows you to have a much better view of what's going on for your system because you have defined targets. You know if they go down because you're pulling metrics from them actively. But you have to run it mostly local to where you're running your servers. There's some kind of static config usually, or originally. There is some service discovery patterns, but if you're using it like just to scrape metrics from like EC2 servers or something, a lot of times that's just configured statically. And on the push side, this was, I think, kind of the traditional model. You have a system running someplace, and any systems that are running can just push metrics to it. So the pros from that side are you don't have to worry about configuring what you're getting data from, but it makes scaling a challenge because you have no idea who's sending metrics to you. Your system could get overloaded very easily. You're kind of relying on people to be honest with what they're sending, or you kind of have these challenges with scaling that out. So I'm going to show a couple different patterns that kind of we explored and some of the kind of pitfalls with those. And I'm going to use Prometheus for the examples. And then I'm also going to use this tool called Avalanche, which is a time series load generator, to kind of show off some of the demos. So back to the picture diagram stuff. So in the example, you're going to see there's 4 EC2 instances running in AWS that are running Avalanche, that are just generating metrics, and they're available on an endpoint for Prometheus to scrape. And then there's 2 Prometheus servers configured identically in a high availability pair that are scraping the metrics from these servers. So hopefully this video works. So don't worry about reading too much of the text because I know it's probably small, but I'll kind of point out things to pay attention to as we go. So what it's showing here is just going through that there's 4 of those Avalanche servers running. This type that we're going to use for service discovery. And then the last 2 things are the 2 Prometheus servers. So we'll jump over to the Prometheus interface and really just show that the targets are configured to show that they're showing up and they're up. That's the green part that says up, and that we're getting metrics, which I'm going to type it in the video in a second. This is just showing the configuration that I'm using the EC2 service discovery mechanism, and metrics are getting pulled. We're going to look at the graph to show that there's some lines, the data is showing up. No need to read that stuff like I mentioned. Okay, so I was showing basic example 4 instances of Avalanche running and Prometheus scraping them. So that could work really well for you. It probably would scale well, assuming that the things on the left, the real servers that you're running out Avalanche, are bounded. The amount of metrics they're going to send are relatively static. But the thing that's kind of a pain is if you were to scale that out, you could use some type of service discovery mechanism like we were using. But if those systems are being run by another team and you don't control how much they're going to scale, you scaling your servers out because of those configuration could become a challenge, or it could cause them to go down because you're pulling too many metrics now. And I think the manual reconfiguring is the thing that we found to be kind of the biggest challenge. And there's no auto clustering or sharding in Prometheus, so you have to, if you want to scrape more metrics than those 2 servers can handle, you're like creating another pair manually. So what happens if we want to push instead of pull? So let's kind of flip the arrows here and change up the way we're running Avalanche. So we're going to use Docker instead so that the scaling is a little easier. Well, Docker doesn't make it easier, but we're going to put it in ECS, which is AWS's Elastic Container Service, and run them as containers, and that way we can just push buttons and scale them easier, and they're going to push the metrics to Prometheus instead of Prometheus pulling. So here's another video real quick. I'm probably going to pause it throughout because it's going to go quick. So we've got the 2 Prometheuses running. Again, no Avalanche servers running here, though. They're not running in EC2 anymore. I'm going to jump over to the targets and just show that Prometheus doesn't know about these servers. The targets are empty. And then we're going to go over to ECS. Don't worry about too much of the detail here. This is essentially AWS's kind of customized pre-Kubernetes way of running container orchestration. So we're going to create 2 services that run a bunch of containers in Fargate, which lets you not have to worry about running the servers yourself. I already created the task definition, which lets you or tells you how you want to run Docker and all the configuration needed. So the containers are configured to send the metrics, the Avalanche metrics, from the servers themselves to the 2 Prometheus instances directly. So we're going to run 4 containers in each service. So once this is done, the tasks should come up. We'll see that there's 4 running. I created a second one in the background. Not while we were waiting, but I edited the video so it'd be shorter. So we've got 8 total containers running. So we'll go over to Prometheus just to show that we're getting metrics in again. These are fresh new instances, not from before. We'll see that we're getting data in over the last 15 minutes. Again, don't worry about reading the text too much. So that is great, right? If the Prometheus is getting the data, fine. But what happens if we want to, or one of the services scales without us doing something based on some auto-scaling logic? So we're going to increase the tasks from 4 to 12 on one of the services just to see what happens. So once this is done, we're going to show that the tasks are running, and then we're going to jump over to Prometheus, and I'm going to sum one of the metrics by a label. and that label is unique to each container running. And what that's going to show is, like, I'm getting metrics originally from 8 things, now I'm getting them from 20. So I'm typing that in now, and it'll just reduce the number of lines, and it's just grouping things in PromQL. So we missed it for a second, but what it showed was there was 8 and then it jumped to 20. So we're just going to go back and show that those 20 are running. This is one service, so there's 12. So what's eventually going to happen, and I sped all this up, but if you look at the bar up here, the address bar, it's blue, it's loading, and that's just going to sit there for like 5 minutes, and it's never going to return because Prometheus is struggling to keep up with the data that was running through it. And if we go back over to the tasks and we look at the logs for one of them, what we see is that the requests getting sent started timing out because that Prometheus server went down. So this is just illustrating that those servers got overloaded very easily. You know, in a real world example, they might be sized a lot bigger, but there's a point at which it can't receive enough metrics and keep everything in memory, especially if people are also querying it for stuff. So in this example, we took that, we scaled it out, and one of the servers fell over, as we saw. And in reality, when I went back and looked, they both had fallen over because they're both getting the same number of metrics. So what's maybe a slightly different way we could run these to kind of address some of these problems? So I think I showed this picture earlier, the same one. This is kind of the Prometheus model. And one of the things that's kind of worth pointing out is that this Prometheus agent, or agent mode, is something that's a new addition to Prometheus, which allows it to run without storing data locally. So it's essentially acting as a scraper, and then it has the ability to remote write the data out to some other service. So the only data that it's storing is in its write-ahead log for the amount of time it takes to write it out to some target thing. And the target thing could be another Prometheus. It could be another open source project around Prometheus like Thanos or Cortex, or it could be a SaaS product like Datadog or the AWS managed Prometheus service. But this model lets you run Prometheus locally, maybe in Kubernetes or ECS or wherever, do the scraping and not have to worry about storage. So it makes that horizontal scaling easier. That's more difficult traditionally with it because it's storing everything locally, and then kind of push everything out. So what the model kind of changes to is we're using Prometheus to scrape the data again. Prometheus is now running in a container though as well because you don't have to worry about storage, and you're pushing, remote writing the data out to some external service. This does mean that you're kind of punting the decision a little bit to somebody else to worry about scaling for pushing, but I mean that's oftentimes what we pay SaaS vendors for. Or you can run that somewhere else, maybe in a centralized data center someplace, and put it behind a load balancer and just think about the scaling challenges of that centralized thing much different than you would locally where you're monitoring and you want to do alerting. One of the benefits of doing this scraping and monitoring locally is that you're as close to the services that are running as possible. So if something goes wrong, you're getting the alerts immediately. If you were relying on pushing the metrics out across some network boundary, if that network connection goes down, then you're kind of blind to what's going on within the service, so that it kind of gives you the benefit of the local scraping model and also the benefit of the remote write. So how does this avoid some of the kind of auto-scaling pitfalls we talked about? So Prometheus has one of those long startup times, like I mentioned, because if the service goes down and you bring a new server up and you may say you reattach to an EBS volume or the disk, it's got to read the history of all of the write-ahead log from the last time it fell over, and I've seen it take like 20 minutes for that to happen. So now you're just kind of waiting for it to read, depending on how much data it got. So this avoids that. It also avoids regional outages because we're local scraping. So if the region goes down, you don't have to worry about scraping the service that's there because it's also down. Whereas if you're outside of the network boundary and you go down for some reason, you're not going to get metrics for that service. And this pull and push model at the same time, kind of offers a little bit of auto scaling and a little bit of constant work. It's not perfect, but I think that's at least how I had been thinking about it. But again, we're pushing some of the storage off to a third party. So just wrapping up some of what I talked about, So look for areas where constant work patterns could alleviate traditional scaling issues for you or the systems you work on. Avoid pitfalls like cascading failures and strive to be anti-fragile. So I put some references here because I know the slides will be up online. These are, they're at the bottom of the slide, so a lot of things I mentioned or talked about is covered in a lot of these blog posts. They're kind of good resources to read more about systems that follow these patterns. And I think that's it. Thanks, everybody.